Hello everyone, my name is Zhao, a master student from Shanghai Jiao University. The work I'm gonna share is RECANS Low Latency Network Function Chains with Hierarchical State Sharing. Let's first see the background. I believe many of you are familiar with network function virtualization, so I will not cover it here. In brief, NFV advocates to implement the hardware-software network functions as software applications running on commodity servers. A great benefit of NFV is elastic scaling, which means that we can dynamically change the number of running instances. For example, when the traffic increases, we can add a new instance, update the forwarding rules to split a portion of the traffic to the new instance. In this way, the number of running instances can match the changing traffic. But sometimes, simply adding a new instance is not enough, because most network functions are stateful. They keep state, and this brings problems. Let's take this thing as an example. Instance 2 doesn't hold the required state, so it cannot process the flows that are originally processed by instance 1. What is the state in NFs? It can be basically categorized into two types, according to whether it is required by multiple flows. Therefore, we call the two types per-flow state and cross-flow state. Typically, multiple instances don't process the same flow, so that the per-flow state can be partitioned across instances. Unlike the per-flow state, the cross-flow state is required by multiple flows. For example, the pool of the available port in the night. To realize elastic scaling of stateful NFs, the two types of state must be managed properly. In other words, NFs must be able to access the required state during the scaling event and after the scaling event correctly. But the performance requirements of some services are increasingly stringent. This table lists several types of services and their latency requirements. We can see that many of them require a latency below 1 millisecond. The latency is critical for the quality of some services. It is very challenging to realize elastic scaling while meeting such low latency requirements. Next, let's see some of the prior state management work and see why state management is challenging. First is the local store approach. In this state management approach, state is distributed across the NF instances, and the state is naturally divided into local state and remote state, according to whether it is in the local memory. To access a remote state, the framework will first migrate the state to the local memory. Since the instances store state directly in their local memory, there is no penalty to access the local state, and no extra resources are needed. But on the other hand, to access a remote state, the state migration is inevitable. Another approach is to exploit an external database, and the instances store all their state in a remote database. In this case, the database is responsible for managing the state and can naturally preserve requirements such as consistency. As the state is not in the local memory, the instances become stateless and can be easily added or removed. Also, in elastic scaling, no state migration is needed as all the state is available by requesting the remote database. However, since all state access is a remote RPC, the penalty of processing packet is big. C is the state-of-art framework of this approach. It mitigates this problem by adding a cache layer between the instances and the remote data store. In this way, the instances access the cache in local memory most time. However, during elastic scaling, the cache of the new instance is empty, and every access turns out to be a cache miss. So scaling events still compromise performance. After analyzing the prior work, we find that state migration of state sharing still incurs high overhead, especially on per packet latency. Fundamentally, the high latency is caused by the network round trips. In this perspective, the two approaches share the same bottleneck, which is the remote access to another instances or to the external database. Let's imagine a more practical scenario. The NFs are often connected to form a chain as a single NF is not enough to implement a complex service. In this case, the latency overhead when scaling out the NF chain can be magnified. For example, when adding an NF chain and send a packet to the new chain, let's see how many times of remote accesses are needed. We can see that the number of remote accesses can be linear to the length of the NF chain. An NF chain typically consists of 3 to 6 NFs, but sometimes as the services become more complex, the length can grow up to 10 or more NFs. With 3 to 6 times of remote accesses latency added to the normal packet processing time, it is harder to meet the performance requirements. Since state migration incurs so much overhead, can we avoid state migration or remote access during scaling events? Let's think about the fact that NFs are no longer hardware, but applications running on servers. So some instances are co-located in one physical server. If we are starting a new instance in a new server, we need to migrate the state from the original instance through network, and the network runtime trip contributes to most of the latency increase. But what if we start a new instance in the original server? If we still use network to migrate the state between two NF instances, we get suboptimal performance because we can use inter-process communication methods to migrate the state. Inter-process communication is typically faster than inter-server communication. Or can we actually avoid state migration by sharing state between the two instances? Using shared memory, in this way, the overhead of remote access is minimized. A quick review of the three challenges. First, the remote access is not quick enough, and chaining NFs further magnify the latency overhead, and state migration during local scaling needs to be eliminated. To address these challenges, we propose RECANS, which uses a new hierarchical state management approach. Locally, all data is stored externally in the node store, which is kind of like the external store approach. But the node store is co-located with the instances. The node store shares state with all local instances using shared memory. By mapping the required data to local virtual memory, an instance can access the state with no performance penalty. Globally, the node stores constitute a distributed address space, or in another word, all the state is distributed across the node stores. And they are managed through a two-layer k-object space, which is inspired by S6. During elastic scaling, the state is repartitioned across the node stores through state migration implemented with RDMA. With carefully chosen RDMA primitives, the state migration latency is minimized. But one thing to be noted is that, unlike S6, the state migration is independent with address space reorganization. Because only when changing the number of node stores does the address space reorganize. To accelerate NF chains, the node store is also designed to be aware of how the NFs are connected, so that they can optimize accordingly. With flow tables tailored for NF chains, the node store is capable to provide chain-wide batch operations. We will explain this later. Let's see a summary of the differences between RECANS and prior work. First, by using shared memory to share the state between the node store and local instances, RECANS avoids remote access during local scaling. Second, by using RDMA, the latency of remote access is greatly reduced. Third, by optimizing for NF chains, RECANS mitigates latency overhead during scaling NF chains and accelerating NF chains during normal time. Next, we will discuss about the design of RECANS. First, let's see how RECANS realizes elastic scaling. Let's have a quick understanding of the hierarchical scaling approach. When scaling, the new instance first finds the required state in the local node store. If it is not found, the instance initiates state migration process and migrates it from a remote node store to the local node store. How the instance finds the location of the remote state is similar to S6, and we don't cover the implementation details here. Then let's see what the node store is like. When start up, the node store daemon process creates a shared memory zone by allocating huge pages, and all the state data is stored in the shared memory zone. Basically, the shared memory zone is divided into three areas: the flow tables, the state objects, and the shared structures. The flow tables are used to store per flow state. A flow table is a hash table indexed by the 5 tuples, which are some fields in the packet headers, and the state objects are used to store cross-flow state. Also, the node store uses shared structures like message range to communicate with the local instances. So how to share the state between instances? Two instances can map the same data structure into their local memory, so they can both access the state in it with minimal overhead. This mapping process is only required at the startup of an instance, and is rather quick compared to state migration. Shall we use logs to protect the data structures? For per flow state, it is not necessary because different instances access different state. With flow affinity, a flow is not processed simultaneously by multiple instances. If flow affinity is not preserved, logs are then needed. But how can we share cross-flow state? Are logs inevitable? It depends on what type of state we are going to share. We find that different types of cross-flow state have different requirements. But there are some common types like numbers and resource pools, so that we can optimize for them. For example, for numbers like packet counters, what we often do is to increase or decrease the packet counter, so we can offload such simple operations to the NIC to save network round trips. We provide 3 cross-flow abstractions. We are going to introduce one of them, the resource pool. We use the split and share approach to share the resource pool. From an overview perspective, we split the resource pool into several smaller pools. Each node store maintains a pool, and the local instance shares the elements in it. If the pool is drained or filled, the elements are dynamically migrated across the pools to maintain a balance of available elements. Next, we will see how we accelerate NF chains. Let's think about this thing. When a packet traverses a chain of length 3, we can see that the path of the packet is actually determined. And when the state of flow 1 in table 1 is accessed, we can infer that the state of flow 1 in table 2 and 3 will be accessed. But as the packet traverses the NF, each NF needs to match the 5 tuple to find the state. How can we fix this? Actually, we can avoid redundant 5 tuple matching by combining the 3 flow tables into one aggregate flow table. In this way, multiple table entries can be indexed by one 5 tuple matching. When the first NF looks up the state, it tags the location onto the packet. When the next NF tries to access the state, they don't need to look up again. This brings several advantages. The structure provides good locality. State of the same flow is stored contiguously. And this also benefits state migration. With one RDMA read, we can migrate multiple states. The lookup and state migration can be performed in a chain-wide fashion. However, in practical, NFs can also be connected into graphs. How can we optimize for NF graphs besides simple chains? Take this NF graph as an example. We can first break it into several simple NF chains. For each chain, we construct an aggregate flow table. We then connect these tables according to how the chains are connected. By doing so, we cover all the possible state access sequence of the packet. More details can be found in our paper. Finally, let's see how to choose efficient RDMA primitives. Due to time limits, we only talk about the principles we follow to choose RDMA primitives. We leave the details in the paper. First, if the remote address is known, we should use one-sided primitives, because they have lower latency and don't involve remote CPUs. Second, if the operation involves a complex RPC, using two-sided is generally better, because it is generally very difficult to implement complex RPCs using only one round trip of one-sided primitive. Third, if the operation is very simple, like fetch and add, we can offload it to the NIC rather than implement a dedicated RPC. Next, let's see whether the evaluation matches our goals. We use two servers each equipped with a Mellanox Connect 5 NIC. To test the elastic scaling, we use the static traffic, which simulates flow arrival rate and packet sizes of real-world traffic. First, let's see a worst-case applicational performance of RECANS. Because the normal case traffic shows no observable throughput decrease. To generate a worst-case traffic, we minimize the flow locality. We generate packets from the flow pool in a round-robin fashion, so that the flows migrate back-to-back. In this case, the flows are migrated intensively when a new instance starts. In this experiment, we test both local scaling and cross-server scaling. Initially, there is only one NAT instance running on server 1, and the packet sending rate is 1 Mbps. We then gradually increase the packet sending rate and scale out when an instance is about to overload. At 0.1 second, a second instance is launched on server 1, and we split the traffic between the two instances. The second instance can immediately process packets, and there is no observable performance decrease. This is because there is no state migration due to the use of shared memory. We then start a third instance on a remote server. This instance needs to migrate state from server 1. We find that even the instance migrates state intensively, the throughput only drops about 4%, and the 99 percentile latency shows a transient peak because of state migration, but the latency peak is still below 1 millisecond. Then, let's see a macro benchmark. We test the per packet latency of two state migration solutions. The first is a full migration path. The NF first finds where the state is stored and then migrates the state. The second directly migrates the state because the location is known. As shown in the figure, when migrating 1 kilobyte state, the median latency is less than 5 microseconds. And this latency is 20 times lower than that is reported by S6. This figure shows the state migration cost during chain elastic scaling. We find that without batch migration, the state migration cost grows linear to chain length. But with batch migration, the cost is basically not changed when the length grows. We can save 94% of the state migration cost when the chain length reaches 10. In Concurrent, RECANS is a new state management framework that targets to realize elastic scaling of stateful NF chains. It exploits shared memory and RDMA to realize state sharing in a server and across servers with minimal overhead. RECANS is also tailored for NF chains. It builds chain-aware aggregate flow tables to provide batch operations that can accelerate both normal access and elastic scaling. Thank you.